Good afternoon to Shubham Tiwari and all the students. Today we have Shubham Tiwari with us for the organized the AICT organized AICT sponsored Prerana scheme lecture. Okay, so I welcome you, Shubham, and
Thank you very
uh,
much, ma'am.
I will delighted to introduce you, Shubham Tiwari. He has done his Masters of Technology in the Mechanical Engineering Design. He worked on projects like design and fabrication of high temperature zone, air conditioning system, phase detection, and tracking for humanoid robot, simulation and path planning of a 6-axis robotic arm for tree planting. I welcome you, Shubham Tiwari. Please continue with your lecture.
Thank you very much for the kind introduction, ma'am. Let us just start our. Uh, Let us now start our session. I will share my screen in a moment. Okay. So, as ma'am introduced myself, I am a my name is Shubham Tiwari. I am student of the same college. I have cleared GATE in the year 2016, 2017, as well as in 2018. Since then, I have been teaching for the GATE examination, and today I feel obliged to the Anjuman College for providing me an opportunity to teach you guys the subject of heat and mass transfer. So let us first start by looking out the syllabus. So the we know that the GATE syllabus has been wait a minute, I will just change the ink. Okay. So the GATE syllabus has been divided into 4 sections. The first one is general aptitude and engineering mathematics, along with applied mechanics. Then we have fluid and thermal, and finally manufacturing and production. The subject of heat transfer actually falls under this category, fluid and thermal. In the GATE examination, this section has a combined weightage of 28 marks, and the remaining 3 sections can be said to be equally divided with 24 mark of each uh, weightage. So what I have observed since 5 years is that heat transfer is asked for a minimum of 3 marks and a maximum of 9 marks. So this is a pretty important subject for us. So as if you will check uh, any official syllabus, this is how the syllabus of heat transfer looks. So this is kind of hectic to understand us, and student may get confused about what to study and what to not. Let us just break it down simply into 6 chapters. So we know that there are 3 modes of heat transfer. First one is conduction, then convection and radiation. Now we have to study this mode of heat transfers along with the 3 chapters like lumped heat analysis, heat transfer through fins, as well as heat exchanger. So these are the 6 chapters that if you study, you can score this an average of 6 marks in the GATE examination. So this is a pretty important subject for us. So without wasting further much of a time, we will start with our discussion today. So what is heat transfer? Heat transfer is flow of heat from one point to another point. So heat transfers from what causes the heat transfer? So there is this plate we have here, the temperature T1, and here the temperature is T2. If T1 is greater than T2, the heat will flow towards temperature T2 until T1 becomes equals to T2. So what caused this heat transfer? This heat transfer was caused due to the temperature difference. The first statement here says that conduction generally occurs in solid on account of the temperature difference. In general, the heat transfer occurs on basis of the temperature difference. So this is the point that is basic to this subject. After that, how heat is transferred in the conduction mode. So in conduction, the heat can either be transferred with the help of molecular lattice vibration or by means of transfer of free electron. Let us see what is the molecular lattice vibration. As discussed above, that was our plate. Now I will take some microscopic view of this plate. In this view, we can see that these are the molecules of the plates, and this is the lattice structure, how it is distributed in the plate. When I transfer the heat, this molecular lattice gets excited and it starts vibrating. When it vibrates, it collides with its neighboring molecules, or let's say molecular lattice, and after that, during that collision, the heat is transferred to the neighboring molecules. In the similar way, the heat can be transferred from point T1 to T2 if we are talking about the molecular lattice vibration. Now, we also know that heat can also be transferred with the help of free electron, as this was at molecular level. But when we go to the atomic level, that is a further small level, the heat is transferred by means of free electrons. So when we provide heat to an atom, what it will do, it will simply pass its free electron to the neighboring atom. So in the similar way, the heat transfer, or let's say conduction, can be occurred by two means, either by molecular lattice vibration or by means of free electrons. Now, it is a very well known fact that the metals, all the metals have ample amount of free electrons. That's why they are very good conductor of electricity. So since they are good conductor of electricity, they possess free electrons. That means they should also be good transfer of heat. That's what our third statement says. All good conductors of electricity are also good heat conductors due to the presence of free electrons. So this is what this is the reason why all the metals are good conductor of heat as well as electricity. So does that mean all non-metals which do not have presence of free electron are bad conductors? The answer will be no, because there is another factor that causes heat conduction, that is molecular lattice vibration. Now what is this molecular lattice vibration? We have seen it. But there are some non-metals like graphite, quartz and diamonds. These non-metals cause uh, these, these non-metals have perfect crystalline structure. We know diamond has a perfect crystalline structure. So whenever we transfer heat through it, it turns out to be a very good conductor. So remember this point. There are some non-metals that are good conductor of heat, and rest of the non-metals have amorphous structures. That is why they are not good conductor of heat. So let us move further with our own chapter. Hmm. So we know that every mode of heat conduction is governed by a separate law of its own. So conduction have its own law known as law of heat conduction or Fourier's law of heat conduction. Now what does this state? Let me just read out this statement for you. So this states that the rate of heat transfer, what I will say is that, let's say Q is the rate of heat transfer through a material. Now this, we have a slab here. So if Q is the amount of heat passing per unit per second through this wall, so this heat transfer according to the heat conduction law is proportional to the negative gradient in temperature minus dt by dx. So this is the temperature gradient. What is temperature gradient? Let me assume that this is a small section through which I have to analyze the heat transfer, whose thickness is dx, and the temperature drop around this section is dt. So the temperature gradient will be dt by dx, and as per the law we have to take the negative gradient. And along with that, there is area also. proportional to the negative gradient in the temperature and to the area. So this is what our Fourier's law of heat conduction says. Now to remove this constant, this proportionality sign, we have to introduce a constant, let's say K minus minus K dt by dx times A. Now this K is known as thermal conductivity. So what is thermal conductivity? Let us just understand this concept deeply, because it is of very much importance for our calculation purposes. So the word thermal conductivity refers to the ability of a material to conduct heat. If a material is a good conductor or not, you have to determine that. Then it can be done only by looking at its value of thermal conductivity. Suppose we have a material which has a value of K equals to 100, and another material which has a value of K equal to 50. So by looking at this value, we can and by knowing the definition of K, we can say that this material is better conductor. Why? Because K has a what is the significance of K? K means that it is the ability of that material to conduct heat. I hope it is clear. Now just look at towards the unit, how it is. What is its unit? Q is equals to minus Ka dx. By rearranging this, we can write divided by A into dt by dx. Now put their units and do the maths. You will find that its unit will be watt per meter Kelvin or watt per meter degree Celsius. Just put their units here and you can solve it by your own, and you will find out that the unit for thermal conductivity is either watt per meter Kelvin or watt per meter degree Celsius. Now Kelvin or degree Celsius, both are same, because we are talking about delta T, that is temperature difference. The difference value will be same for both the units, either Kelvin or degree Celsius. So there's no need to get confused over this thing. Now we know that good conductors have good conductivity and insulators have very low thermal conductivity. We also know that the matter can be divided into solids, liquids and gases. And to be a good conductor, you either need free electron or crystal lattice. So both of these are present in solids in ample amount, because most of the metals are solids, and some non-metals which are solid have possessing this property of perfect crystalline structure. So this means that the thermal conductivity of solids is greater than that of liquid, and it is greater than that of gases. Now when we talk about gases, one thing you must understand is that the thermal conductivity of gases is temperature dependent. That whenever we increase the temperature of gas, let's say in this container we have gas and we are heating it with the help of burner. What happened to this? That the atoms and molecules of these gases will start moving violently, and in doing so they will uh, collide with each other, and this collision will cause the heat to flow or the heat to get conducted. So the statement here can be justified that the thermal conductivity of gases increases with the increase in temperature. Now liquids are better conductor of heat as compared to gases, that we have seen. Among liquids, mercury has the highest thermal conductivity, that is no doubting there, because mercury is a metal, it has free electrons, so it has to be the liquid with highest thermal conductivity, and this is the final point. So if there's any MCQ question that you come across and you find that which of the following material has highest thermal conductivity, so diamond has the highest thermal conductivity, followed by metals, and among the metals lead has the smallest among the metal lead has the least thermal conductivity, followed by ice, then followed by glass, water, plastic, rubber, oil, and finally air. So what you have to remember is this: air, diamond, lead and metals. So this will be actually very helpful in solving MCQs that are memory based MCQs. This is very helpful. So please try to remember this. Okay, now moving towards a very key concept of electrical analogy. Actually, this concept is going to help us a lot in the conduction, convection as well as radiation chapters, because our problems that we are going to solve, we can simplify it by drawing simple circuit diagrams, just like in the case of electricity. So we have studied in the school that let us suppose that this is a circuit, electrical circuit. This is a battery connected to it. The circuit is closed as the key is closed, and due to the potential difference V, the current will flow from higher potential to lower potential. And there is a very well known formula that current is equals to the ratio of voltage divided by the resistance provided by this conductor to the flow of electrons. The V is what? Potential difference. Potential difference. And R is what? Resistance. Electrical resistance to be precise. And I is electric current. Now, electric current is also flow of electrons that we have discussed earlier. That the flow of electron is caused due to the potential difference. Now let us just jump towards our mechanical stream and find out what we have to study. We are studying here conduction. We know that heat transfer occurs because of temperature difference. Temperature difference. Okay. Here we had potential difference. Here we have temperature difference. The wall at this point is at temperature T1. Here it is at T2. T1 is greater than T2. So there is a visible temperature difference. The heat will flow from high temperature to low temperature, just like in this case that the electrons were flowing from high potential to low potential. Here the heat will flow from high temperature to low temperature. So now we know that flow of heat, the heat flow rate is equals to what? Here we had potential difference, here we will have temperature difference. Now here is an interesting term, thermal resistance. This term actually signifies the resistance that this metal, or let's say conductor, in a more generalized way, a conductor that will resist the heat of flow, the amount of resistance is known as thermal resistance. So what will be its unit? So let us just rearrange it. We have delta T by Q. So delta T is Kelvin or degree Celsius. We will write Kelvin per watt. So this is its unit, whereas it has the unit ohm. So when we can just let's say when we just uh, idealize the heat transfer system as an electric circuit, it becomes more easy to solve, that we are going to see in the coming sections. So yes, here we have a slab. Here we are going to look the thermal resistance part in more detail. So what do we have here? We have here a slab. Okay, that's fine. This slab has a thickness of length L. Thickness L. The cross section area here has the value A. At this point we have temperature T1 and here we have temperature T2. So T1 is greater than T2. Now I told you that if we convert this thing into an electric circuit, this will be more easy for us to solve. So yeah, sorry for my diagram, I'm not a good painter. My drawing skills are bad, but you have to bear with it. So yes, here the temperature is T1 and here we have temperature T2. Between these 2 points, this material will provide the thermal resistance R. Since the shape is slab shape, so we will say it R slab. Now we have to find out this. So first of all, let us just consider a small section. That's a normal procedure in every engineering problem. So yes, okay. So this is a small section we have. This small section has a thickness dx as seen earlier, and the temperature gradient along this small plane is, let me try to write it here, dt. So with the help of Fourier's heat conduction law, we can write Qx is equals to minus Ka dt by dx. What we can now do with it is rearrange the term Qx is into dx, or simply let me just erase this x, that may cause confusion. Okay, so q into dx equals to minus k a dt. This is how we can rearrange. Now I want to integrate this, because this was written for this small section. Now I want for this entire slab. So how we can do it? We have a very normal procedure of integrating this equation. Yes. Now it's time to put limits. So here the x has a value equal to 0, and here x has a value equal to L. So we can write x is varying from 0 to L. And what is the direction of heat transfer? It is from T1 to T2. So yes, I will write here T1 to T2. Now let us integrate. By integrating, I can write QL is equals to minus KA T2 minus T1. Now we know that T1 is greater than T2, so this value will be negative in magnitude. So that's why we have negative temperature gradient. So if anyone had a certain question that why the Fourier's law said that we have to take negative gradient, because he knew that this value was going to be always negative. Hence, we have to take the negative sign here, and it will become Q Ka T1 minus T2 by L. I can rearrange this equation as Q is equals to delta T upon L by Ka. Now, isn't it similar with delta T by R thermal? So, which means that the resistance of slab is equals to L by Ka. Oh, sorry. Let me draw just a rectangle here to highlight it. Okay, so R slab is L by K. What is L? L is the thickness of slab divided by K is the, actually it was the thermal conductivity of the material of which the slab was made. So if it was made of cement, we have to take the value of K cement. If it is made of steel, we have to take K steel. So the value of K depends on the material. Multiplied by this perpendicular area. Wow, the area is perpendicular to the direction of heat flow. So R slab is L by Ka. Don't worry, we will, if it is not looking good, we will summarize this in the coming section. I hope it is all clear to all now. Okay. Now here, we just seen that the thermal resistance of a slab is L by Ka. But what happens if there are more than one walls? And we know that wall can be arranged like this, or like one after another, or one above one another. So how can we find the thermal resistance, equivalent thermal resistance? Let us consider this case first. Here the slabs have been connected in series. This is material 1 having thermal conductivity K1. Here the thermal conductivity is K2. Here the length is L1, here the thickness is L2. Actually, we get confused with L equal to length, but here it is the thickness of wall. Huh. So let us just draw our circuit diagram. This will be resistance provided by wall 1. This will be resistance provided by wall 2. This is temperature T1. This is temperature T2. It will move from T1 to T2. And in this way, we can write that R equivalent is equals to R1 plus R2, just like we have in electric circuits. So this is how equivalent resistance can be found out. Now in this case, we have a parallel circuit kind of situation. This represents the resistance provided by R1 or let's say wall 1, and here we have R2. So what was the formula in electricity? It was 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2. Now this is equals to, now it is up to you to find out, but this is how we calculate the equivalent resistors for parallel when the slabs are connected in parallel. Okay, now let's move towards the next shape. Okay, so I will not be deriving for this. This is for you guys to derive, but I will give you hint how to solve it. Number one, we have Fourier's law of heat conduction that we have to apply. Then in that case, we took an elementary slab. Here what we will do? Here we will take elementary ring. Wait a minute. Here we will take elementary ring. This ring will have a thickness that had dx, it will have dr. Its value will move from 0 to r. Sorry. Its value will change from 0 to r. Then we will have dt. Its value will be from t1 to t2. We have to put this limit, integrate this, and find out the value. When you are going to derive it, you will find out the value of resistance for cylinder will come out to be 1 upon 2 pi kl ln of R2 upon R1, where R2 is the outer radius, R1 is the inner radius, K is its thermal conductivity derived. Sorry, once again, this will help us. Yes. So if this comes out to be your value, then your derivation is right. But I will say that you must prefer books. There are some good books like Rajput and Tikenag, and there are some good resources available on net as well. Refer those things and derive this for cylinder, and then also derive it for sphere as well, because we can save our time here, and we have to look a lot of other stuff as well. So in a similar way, you solve this for sphere, you will find that the value will come out to be R sphere is equals to 1 upon 4 pi k 1 upon R1 minus 1 upon R2. Yes, R1 is inner radius, K is the thermal conductivity again, and 4 pi is just constant. So this is the value of sphere. Sorry, the value of thermal resistance for a spherical shell. Okay, now let us now see Newton's law of cooling and the concept of convective resistance. Now consider this is a plate that was heated earlier. Now it is kept at a room temperature. Its temperature is greater than that of room temperature. Now I start a blower which forces the air to flow in a direction parallel to the surface of this plate. Here is my blower. This is forcing the air through it, or it can be natural. So when this air passes through, it will have temperature equal to room temperature. Now there is this temperature gradient, or we will say temperature difference, because T1 is greater than Tr. So the heat will be carried away with the help of this air. The heat will be carried away with the help of this air uh, because of this temperature gradient. Now what the Newton's law of cooling says that this is conducted by means of convection. So heat is conducted by means of convection, and Q convection is given as HA, temperature of this plate, minus temperature of this room, or that is temperature of air. Now what is this H? This H is known as coefficient of convection. Its unit is watt per meter square Kelvin. If you rearrange these terms, you will find out. Now let us compare this with our general formula that I told you to remember, that Q is delta T upon R. This is going to help you a lot in this subject. If you get yourself acquainted with this formula, it will help you a lot. Now it is Q equals to delta T by R. We have this delta T, okay. So Q convection is equals to TW minus TR. Now HA can be written as 1 upon HA. Now that means this is thermal resistance of convection. So R convection is equals to 1 upon HA. Now just remember that the area in conduction and area in convection both are different. In convection, the area is perpendicular to the direction of heat flow. It is the surface area with which the air will get into contact, surface area, to avoid any kind of confusion. So let me just highlight it as well. Here it is. So we have found thermal resistance for slab, for cylinder, for sphere, and now for convection. So there is going to be thermal resistance, be it conduction, convection, or radiation. So the medium will, be it a vacuum or open space, it will provide some sort of resistance. Nothing is going to be 100% transmission efficiency. There is not going to be such kind of thing. So the heat, wherever there will be heat transfer, there will be going to be some losses, and which are accounted by this resistance. Okay, now there is this important concept of critical radius of insulation. Now most of us know that actually we provide insulation for heat to avoid heat transfer. That is our general conception. But what if I say that you can also provide insulation to increase the heat transfer? No, the general thinking is that everyone can tell that insulation is provided to avoid the heat transfer. But I am saying that it can also increase the heat transfer rate, and so is the next concept of critical radius is same. Now here we have a cylindrical pipe. Now we decided to put some insulation over it. Okay, this is some insulation. We can make it better by using, just give me a moment. Okay. So this is Okay, our circle is gone. Wait a minute. Yes. So this is the layer of insulation we have provided. Now by providing so, what we have done is, knowingly or unknowingly, we have increased its surface area. The surface area of this entire wire has been increased, and we know that our convection is equals to 1 upon h into area surface. When the surface area increases, the convection resistance increases. Now let's see what are its implications. Let me draw a circuit diagram for it. I will just take this half of it and I will draw a circuit diagram. So here is we have the material 1, here we have insulator R2, but this is for convection, okay. And then will sorry, this is for conduction, and outside it will be okay. This is the resistance by insulating material, and this is the convective resistance. So total heat transfer will be Q conduction plus Q convection. Now what is happening here is the R convection is decreasing because we have increased the surface area. So this will what have, so we know that if Q is equals to delta T by R, so if this decreases, this has to increase. So the convection heat transfer increases, and because of this the heat transfer increases. It goes on increasing. Let's say this is on y-axis we have uh, heat transfer Q, and on x-axis we have thermal resistance R. So as I told, it will keep going on increasing. But what happens after a certain amount of time? This is an insulating material. So even though convection has decreased, but the thickness has automatically increased its conduction. It has increased the conduction resistance. So after that, if we go on increasing, its heat transfer rate keep falling. So at this point, it was maximum, and this point is known as critical radius of insulation. So the definition here says that the radius of insulation at which heat transfer rate is maximum is called as radius of insulation. Sorry, critical radius of insulation. So RC is the critical radius of insulation where the heat transfer rate will be maximum. Now, very interesting questions get asked on this type of question, on this topic. So say if you are provided with steam tube, so in a steam tube, what we want that heat should not go out. This is no. We have to avoid this. So what we will do, we will provide insulation, but we have to also make sure that it should not be maximum heat transfer. We need it minimum. So what we will do, we will keep the radius of insulation greater than critical radius. So we will put it into this region. After that, we have an electric cable. We have electric cable. About this cable, we don't want a lot of heat to actually stay in it, because if such stays, that will not be good for electricity to conduct. Can be short circuit, or the wire may get broken in that. So that is what we want to avoid. So we want that heat has to go out of this wire or cable. So what we can do is to try and put the radius of insulation in this zone. So cable will stay in this zone and steam tube will stay in this zone. So let me Just say for cable, radius of insulation should be less than critical radius, and for steam tube, radius of insulation should be greater than critical radius. So this is a very important topic that gets asked, and a very practical one, so that one can understand why it is necessary. Okay, so now the next concept is of, okay, what are the formulas for? I am not going to derive it again here. Just try and remember it, because the GATE exam is objective based exam, though it does not ask here derivations, but derivations are a very important part of your preparations. You have to prepare for derivations, otherwise you will not survive in GATE exam. uh, Derivations, because questions may not get directly put the value and get the kind of questions. The questions are like, you have to derive some quantities and derive some formulas based on the parameters. So going through derivations is an important aspect of GATE preparation. So let us come back to our concept of critical thickness. So we will either be facing a cylinder or sphere. A sphere can be shell, and a cylinder can be cable, wire, etc. Anything it can be. So critical thickness of insulation for cylinder is K upon HO, and that for sphere is 2 times K upon HO. Now this K is the conductivity of insulating material, and there will be outside air in it. So HO is the heat transfer coefficient for outside fluid. So again, these two are very important formulas. I will put it here. This is what we have to highlight. So for sphere it is K upon HO, and for for cylinder it is K upon HO, and for sphere it is twice K upon H. Don't get worried, we are going to solve some numericals based on this concept, so that you can score at least 2 marks on these topics that get asked, if it gets asked, that because no one can say what can be asked in GATE exam. Okay, now this is the final thing that we have here. So this is the general conductivity of in cylindrical and polar coordinate also. So I am just showing you this Cartesian coordinate equation, and I am that too. You have to, that is your homework, to derive this equation. Just refer some standard books that are mentioned, that I mentioned earlier, and try to derive this, because this gets derivation based question asked very much on it. And if you are preparing for engineering services, this is very important practice to go through derivations. Okay, so what is the equation we have? What is the general heat conduction equation? It says that 1 upon alpha into dt by dt equals to del square by t plus q triple dash by k. Now what are these things? Let us understand. Alpha is thermal diffusivity. Thermal diffusivity actually tells us how fast the heat is gonna spread into the heat is going to be spread in a material. If alpha has a greater value, the heat will spread at a faster rate. If alpha has a smaller value, the heat is going to be transferred at a slower rate. And what is then, we are dt by dt. So in earlier stages, the temperature was not, we are not considering it was unsteady state, but here the temperature is changing with respect to time, dt by dt. So this is the time rate of temperature, time rate of change of temperature, which is equals to del square t. What is del? Del we have seen in vector calculus. Del is del by del x plus del by del y plus del by del z. So x, y, and z direction, that is the temperature gradients in x, y, and z direction. Q triple dash is internal heat generation. Now, internal heat generation problems get asked when there is a heater put inside a wall. So this is a wall, but we have put some heater in it. So this question becomes of internal heat generation. So this Q triple dash is internal heat generated per unit volume of the wall. And this is thermal conductivity as we know it is. But thermal diffusivity is an important concept. It will going to help us in the future lectures as well. Alpha is K upon rho Cp. K is thermal conductivity. Rho is the density of the material. K is thermal conductivity, and Cp is specific heat. Specific heat because it's metal, and metal has just only one thermal conductivity, C. Not unlike gases which have Cp and Cv. So this is not in the case of solids. So we have to say just it is C. So C is the specific heat of the material, but who knows, you may come across gases as well, but in case of gases it will be Cp, the higher value. Okay, now what were the important formulas that we have to remember? Let's just go back from the earlier slides, what we had studied in this session. The very first thing that we studied was this. Yes, the Fourier law of heat conduction, followed by where is our master formula, followed by this, the master formula of ours, which is going to help us. Then the thermal resistance of slabs, cylinder, sphere, then convective resistance, followed by the concept of critical radius of insulation. So this was our catch out of it. Then we had this of critical thickness for cylinder and sphere as well, followed by general heat conduction. So we will just write down this formula quickly. Number 1 minus K dt by dx. This is Fourier's law, followed by our master formula. This is different. Sorry. So R is equals to, now for slab, it will be L upon Ka. Note down this formula if you need. I think you should note it down. R cylinder is 1 upon 2 pi Kl ln of R2 upon R1. R sphere is 1 upon 4 pi K 1 upon R1 minus 1 upon R2. And finally, we have some more. R convection is 1 upon HA. Then we had R for critical for cylinder, critical radius was K upon HO, and that for sphere it was twice K upon HO. So these were the important topics that we saw in this unit. Now let us just try and solve a couple of problems. So this question was asked in GATE 2016 for 1 mark, and it is pretty easy, pretty easy question. Now, while solving question of this section, fluid and thermal, please trace on each and every word. So it says that steady one-dimensional heat conduction. What does steady one-dimensional heat conduction mean? Steady one-dimensional heat conduction means that the heat transfer will be constant throughout this wall. One-dimensional heat conduction takes place across the faces 1 and 3 of a composite slab consisting of slabs A and B in perfect contact as shown in the figure. Okay, so it says that we have two walls, wall A and wall B. These are of two different materials and these are placed in series. So these two walls are placed in series. You can see in the figure. The figure was provided in question. Okay, so don't need to be drawing this question, this figure in the exam. It will consume time. Now it says using the data as given in the figure, the interference, you have to find out this temperature T2 at this point. So what we can draw is we can draw this simple circuit diagram. This is temperature T1, resistance of wall A, resistance of wall B. This is point 2, here temperature will be T2 and here it will be T3. Now I told you to stress on each and every word while solving the problems of fluid and thermal section. It states steady heat conduction. Steady means that the heat transfer rate is going to stay constant at any instant of time and at any place. So I can say that the total heat transfer from 1 to 3 can be equal to or will be equal to heat transfer from this section 1 to 2. What we can write then? T1 minus T3 divided by RA plus RB, because we are going from point 1 to point 3. So there are two resistances in series, so we are just gonna add them. And then 1 to 2, what is in between 1 to 2? There is just one resistance, that is RA. So T1 minus T2 divided by RA. Now we will put these values, 130 minus 30, it will come out to be 100. Now let us first calculate thermal resistance. RA is what? L by Ka. L by Ka, the area is not given. So anyways, it was going to get cancelled here. So we will take area to be 1 meter square. So L is what? For A it is 0.1. Okay, fine. I won't write down data because that will consume my time. Ka is 20 multiplied by 1. So let us just calculate. So we have our get calci with us. We'll clear this thing. 0.1, sorry, divided by 20. Okay, now it should be 0.005, and R2 RB is equals to 0.3 upon 100. No need to use calculator, used to minimize the use of calculator. So RB will be equal to 0.003. Where is, okay, so we are not going to use anything out of this box. Stays here. So RA is found out to be 0.005 and RB is found out to be 0.003. So T1 minus T3 is 130 minus 30, 100 divided by RA plus RB is 0.005003. It will be 0.008. So T1 is again 130 minus T2 divided by 0.005. We will solve this equation and we will try to find out value of T2. This goes here, 5 by 8 into 100. solve this equation, I think the value will come out to be 130 minus, we have to use brackets in this calculation. This calculator is pretty difficult to use. Get acquainted with this calci. So yes, the value comes out to be 67.5 degrees Celsius. 67.5. So T2 is equals to 67.5. This took me some time here, but you have to solve it in less than 3 minutes. So try and keep practicing this problem because the calci is hard to use. Then here we have another problem. This is pretty easy to solve. Okay, a foam insulation is added to a 4 centimeter outer diameter pipe as shown in the figure. The critical radius of insulation. Now what it wants us to find, the critical radius of insulation, RC. Now it's a pipe, that means cylinder, and for cylinder RC is K upon HO. K is of what? We have here this pipe material and this is insulating material. We want of insulating material which is foam. So it come out to be 0.1 HO. What is HO? HO is 2. 0.1 by 2 is 0.05 meter. But can we write 0.05 meter? No, that will be wrong answer because they have asked it in centimeter. So it will come out to be 5 centimeter. The answer will be 5. Now remember this point, always focus on the units that they are asking. Sometimes what happens, even if you solve this question correctly, but you put wrong unit, then your question will be, then your answer will be considered to be wrong because they give certain range. And if your answer is not within that range, then your answer is supposed to be wrong. So keep this in mind. So that was it for today. I think if you go through this lecture again and again, which is actually a very good feature of so you can score at least 2 marks topic, but that will require you to go through derivations as well as practicing problems. There is no alternative to this. So thank you very much. Let us just end our session here. Thank you for being here. We will continue in the next session. Thank you very much.